Before watching this lecture, you should know about the OLS estimator in the linear, linear regression model with several explanatory variables. So in this lecture, we'll look at the properties of this OLS estimator. We have the following setup. We have a linear regression model with random sampling. We have k beta parameters. So the model looks like this. Yi is a linear function of k minus 1 explanatory variable and an intercept plus a random term. And in this lecture, b1 through bk will denote the OLS estimators of beta 1. The values we get by minimizing RSS. Here I have some simulated data on 3 x variables. These are my betas. This is my standard deviation of the error term. I simulated the error term. I've simulated the dependent y variable. So we can get all the OLS estimators using the linest, the y's, the x's, intercept, and let's do the statistics as well. Shift Control Enter. And remember the first row, those are the OLS estimates. So my my intercept is estimated to 0.66. This 2.7 is an estimator of this one, and so on. And this is calculated from known data. So this is all known to the econometrician. This is all green stuff. Let's look at the Gauss-Markov assumptions in the case when we have several explanatory variables. The following set will actually suffice as the Gauss-Markov assumptions. First of all the explanatory variables are exogenous. Remember, that means that the expected value of the error term is 0 no matter what the x variables are. And xi here is just shorthand for all the explanatory variables for observation I. In my simulation study, it's satisfied. We can see that all these error terms do have an expected value of 0. Next, the residuals must be homoscedastic, so they need to have a common variance, and we denote that by sigma square. That's also satisfied in my simulation study. This is the sigma, the common standard deviation. So the variance of the error term conditional on the data should always be sigma square. So these are the assumptions. These are the Gauss-Markov assumptions. And if we assume this, if we have data that satisfy these assumptions, then the OLS estimator has nice properties. It is unbiased and consistent. So the OLS estimator for all of them are unbiased. And for this to be valid, all we need is the exogeneity. We actually don't need homoscedastic errors to prove this. The test is to look at this and to F9 it. And just have a look at one of them. Doesn't really make any difference which one. Let's have a look at B2 and compare that to beta 2, 2.1. Unbiased means that when I do this F9ing thing, the cell in L9 should on average be 2.1. Sometimes above, sometimes below. Below, exactly equal. Above, equal, below. If you keep on doing that, you can verify the unbiasedness. That just doing this is obviously not a proof of unbiasedness, but it is an indication. Next, the OLS estimators are consistent. If we make the exogeneity assumption, we do need some additional very weak additional assumptions to prove this, but these are typically satisfied, so we're not going to talk about them. But remember that this means that as the sample size increases and go to infinity, the b's will become equal to the betas. So that's the first part. That's the properties of the OLS estimators. The second part is, well, almost equally important. We need to get some kind of measure of how precise these b's are. How close is this 1.18 to the true value of 1.1? And that's captured in the variance of the OLS estimators. So for the variance, in this case, it's possible to show that we can actually find a formula for the variance of the OLS estimators, but just like the formula for the OLS estimates themselves, it will become pretty nasty formulas unless we use matrix notation. But it doesn't really matter because we typically never use formulas to calculate estimates and standard errors. We use software to do it, and it's just enough to know that there is a formula and it can be programmed. The variance of the OLS estimators will be denoted by variance of bj, where j is any index between 1 and k. So variance of b1 is the variance of the intercept, and variance of b2 is the variance of b2, and so on. This is conditionally on x, so conditionally on all the x data, all observations and all the x variables. To calculate this variance, you need all the x data and also sigma square. That's the same as in the one explanatory variable case. The variance cannot be calculated without sigma square. Sigma square is a red variable. We don't know it. So the variance of the OLS estimators are unknown as well. But the strategy is exactly the same as for the one variable case. We don't know it, so we estimate it. And we're going to call the estimator S square in this case as well. So S square is going to be an estimator of sigma square, and we'll use that instead of sigma square in the variance formula for the OLS estimators. So here is one of the few differences when we look at the one explanatory variable case and the several one. For the one explanatory variable case, S square was the RSS divided by n minus 2. We concluded that the sort of intuitive RSS over n minus 1 turned out to be slightly biased, but if we divide by n minus 2, it became unbiased. Now in this case, if I have more than one explanatory variable, that will actually turn out to be biased again. So what I need to do to make it unbiased is to divide by not n minus 2 but n minus k. Remember, k was the number of beta parameters in the model, which was the same as the number of explanatory variables plus 1. So you can see that this formula works even in the case when you have one explanatory variable. If you have one explanatory variable, then you have two parameters. So in that case, k is 2. So the formula becomes RSS over n minus 2 in that case. But this formula works even if you have several explanatory variables. So with this adjustment, doing n minus k instead of n minus 2 or n minus 1, you can show that S square will become an unbiased estimator of sigma square. And under some mild conditions, it will also be a consistent estimator. So S square is still going to be called the OLS estimator of sigma square. Taking the square root of s squared gives us a symbol we denote by s, and that's called the standard error of the regression, just like before. S is going to be a consistent estimator of sigma. So now that we have an estimator of sigma square, we can use that s square in this formula for the variance of bj. And if we do that, we get what we then call the estimated variance of the OLS estimators. So if we replace sigma square with s square in this hidden OLS Gauss-Markov variance formula that I haven't really given you, we get estimated variances. And these are denoted by VAR of BJ with a little hat on top of var to just signal that they are actually not the true variances but estimated ones. Taking the square root of these ones will give us the OLS standard errors, and they are denoted by SE of BJ. So the square root of the estimated variance. Typically, econometric packages provide you with standard errors. Obviously, if you have standard errors, you can easily get the estimated variances by just squaring the standard errors, but the standard errors are typically more useful than the estimated variances, so it makes sense to print those instead. If you do Excel, they're always printed in the second row. So these are the standard errors. For example, the standard error of B2 is 0.07. We can see one thing which we already knew, and that is that for example, the intercept has a much higher standard error than does the slope parameters B2, B3, and B4. It is more difficult in general to estimate the intercept. So all econometric packages will give you the standard errors, and they will typically give you those in the printout next to the estimates of beta to the b's. Finally, we have the Gauss-Markov theorem, which applies to this case as well. And it's this: the OLS estimators will be blue, best linear unbiased estimators, under the Gauss-Markov assumptions. You will not find a linear estimator that is unbiased and that has a smaller variance than the OLS estimator. Let's have a look at how to do OLS with several explanatory variables in first Gretel. It's very similar procedure. You just do model ordinary squares, OLS. You add your y variable here. Only one y variable. If you try to add another one, it's just going to replace it. But it does allow you to add several x variables. So I have my constant representing my intercept. I have sat m, and I can add all the other ones as well. So now I'm explaining the final result using both the SAT math score, the SAT verbal score, and the high school GPA. Click OK. These are the results, the coefficient estimates in the first column here. So this number here, for example, should be interpreted as follows. For a given student, if the student had 1 point more on the SAT M, keeping SAT V and the GPA at the same level, not changing those, then the result on the final exam would increase by 0.06. Similarly, this is the increase in the expected result on the final exam if the SATV increased by 1 unit. Sometimes these are called marginal effects. So this is sometimes called the marginal effect of SATM. but we have to be a little bit careful because when we think about marginal effect, we tend to think about that as a under a ceteris paribus assumption. That is, we tend to think about it as the change in the y variable if I increase SATM and if I keep everything else constant. In this setup, if you have included these three explanatory variables, you can only think of this constant as the effect when you increase SATM by 1 unit, keeping the other two variables constant, not everything else. And the second column has the standard errors, the square root of the estimated variance, and that will give us an idea of the uncertainty in the estimate. We will use that when we test hypotheses, when we create confidence interval, and other types of inference, which will be discussed in a later lecture. In eViews, you do something similar. You can do quick estimate equation and just type the equation you want to estimate. So you begin with the dependent variable final. You have to type a C if you want the intercept, and then you just add the explanatory variables that you want to use. So SATM, SATV, and HSGPA. This would be one way of doing it, the easiest way. You can also do it according to this example specified right above, but this will work fine. And that will give us the parameter estimates in this column here and the standard errors in this column. You can also see that we get the R square and the adjusted R square. Remember, the adjusted R square will punish the measure of fit for adding more explanatory variables. The standard error of the regression, that's the thing that we call S. This is the RSS. This will be the average score on the final exam for all the students. And this would be the sample standard deviation of the final result. All these other numbers will be discussed in lectures